So hello, welcome to the next day of physics. Today we're going to finish chapter 8. Once again, chapter 8 is the last chapter on your next exam, which is a week from Friday. We'll do practice problems on Friday. Yeah, I guess that's all I had to say there. Um, I'm playing with a football today. Why that is, we'll get to later on. So, where we left off is I had just finished covering torques. I introduced the fact that torque is all F sine theta and that the sum of torques is I alpha. Instead of F equals ma, we have torque equals I alpha. Well, I is the moment of inertia, something that is usually a constant for any given shape or can be solved for complicated shapes using calculus, so we can skip that for there. And alpha being centripetal, sorry, misspoke, take that back, alpha being angular acceleration. So, what I want to start today is something completely different and not torque at all. You see, in chapter 5, we said something has kinetic energy if moving in a straight line. But if I take this football and just kind of without spinning it, I'm ignoring a spiral, but just woo. At any given moment, something has a certain amount of kinetic energy of 1/2 mv squared. But that's just something moving, right? Let's talk about if I spin this football. If this football is spinning, and even if it's not really going up or down, if I can kind of just spin it in place, which I can't really quite do without it falling, but ignore that for now. If something is spinning, it has energy. I'm doing work on it by making it do that. Some of that energy is going to spinning, and I'm putting a lot more force to do that than I would just to go, meh. Whoop. And what that means is that anytime something spins, it also has kinetic energy. You see, there's actually two terms for mechanical kinetic energy. We just only did one so far. 1/2 mv squared is the kinetic energy of linear movement. But also something is spinning, it has rotational kinetic energy. And rotational kinetic energy, which I could derive the equation, I'm just not bothering unless you really want to see it, will equal 1/2 I omega squared. And the general idea is, yeah, if something is moving in a circle, if I go and push on this and make it spin, I'm giving it kinetic energy. That kinetic energy will just follow 1/2 the moment of inertia, in this case would be that of a solid disk, times omega squared, how fast it's moving angular velocity wise. And rotational kinetic energy is the same kinetic energy as linear. All of the equations we did with conservation of energy, they all work, they're all true, they still work. It's just really we should have had two terms for kinetic energy, not just one. In fact, the first problem on your exam will be conservation of energy. It might involve rotational because it's just you treat it the same. You deal with work. Work is changing kinetic energy. You can do potential energy becomes kinetic, and everything can be treated the same. In fact, yeah, conservation of energy is still true. I can still say initial energy equals final energy. And just I would not have just linear kinetic energy, but also rotational kinetic energy. Really, this term should also have the 1/2 kx squared of spring potential energy also. That I theoretically, I do add it, I can add springs. We actually have 4 terms for energy. Linear kinetic, rotational kinetic, gravitational potential, spring potential. Now in any given problem, I've never given a problem that includes both spring potential energy and rotational kinetic energy. It's doable. I've thought of one before with a um, pinball, with a pinball game, but I've never actually written it up. Um, but we'll just treat it the same as any other conservation of energy problem. Questions there? Let's do a problem. You see, this was actually written on this slide, I think, and I didn't say it out loud. So I'm going to now say something out loud I kind of skipped. Let's say something is rolling. If something is rolling, whoop, like so, you know. Actually, can I check? I have a video I'm going to play. Let's see if I do it. Do I do it solo? No, I don't. If something is rolling, anytime an object is rolling, it's really doing two things simultaneously. If I take this ball and set it rolling, it is moving. That's going to be the kinetic energy. lineal, 1/2 mv squared, and it's spinning. That's going to be the 1/2 I omega squared, because as it rolls, it does both. It moves across the table and it spins. And so rolling, like so, is going to, anytime we have something rolling in energy, we have to use both equations. Linear kinetic energy of it, and rotational kinetic energy of it spinning. Does that make sense? Okay, let's do a problem. So what this says is we have a hoop of mass m and radius r, and it starts at rest from the height of 2 meters above the table and rolls down a 30-degree slope. What is the linear speed of the hoop when it leaves the incline? Basically, what I have is just something starting at the top of a hill and rolling down it. That is like so. The idea makes sense? Really, if I want to show it, I should just do this. So, starting at the top, rolling down. Okay? If I want to solve for this, I have something changing height, and because it's changing height, changing velocity. Changing height causing a change in velocity, that's conservation of energy. Or at least it always was in the past. And I just realized I should add another sig fig to my 30. It's on this figure though. And so what I can say is that I can make an equation for energy at the top and make an equation for energy at the bottom. I would say at the top. At the top, it's just at the top. It's not, I say it starts at rest, so it has some potential energy due to gravity, but it's not moving if it starts at rest. So at the top, it'll have no kinetic energy. At the bottom, it's at its lowest point. If it's at its lowest point, that's where I'll define my height to be 0, as drawn in the figure. So I can say at the top, it's just potential. At the bottom, it's just kinetic. But this kinetic at the bottom has two components. Lineal, or also called translational. I used a T here and an L elsewhere. I should be more consistent there, so I apologize for that. But translational or linear kinetic energy at the bottom, and also rotational because it's spinning. Now the energy at the top is just potential. That's just mgh. And I'm using a capital M here just because this figure did. And at the bottom, it is doing, once again, two things at once. If it is rolling, it is A, moving across, and B, spinning. That's what rolling is going to be. Is when you roll, you're doing both of them at the same time. So I have the energy of it going whoop, and the energy of it, it's too big for me to palm, and the energy of it spinning. Now, here's the thing. Anytime something is rolling, you can relate V and omega. If something is rolling, its linear speed equals its angular speed times the radius, which means its angular speed is its linear speed divided by the radius. Also, this said, what is the linear speed of a hoop? If I go back a few slides to class Monday, I know the moment of inertia of a hoop was given. It was on one of those tables. The moment of inertia of a hoop is mr squared. And what I'm going to do is I'm going to take omega and I and shove it into my energy equation. I'm going to say this omega goes over, well, the arrows kind of don't go to the right spots, but you get the idea. This omega will go to this omega. This I will go to that I. And so what this really is that the energy at the bottom is 1/2 mv squared plus 1/2 I omega squared. Well, I was mr squared and omega is v over o. But that gives me v over r squared. V over r squared is the same as v squared over r squared. And if you look at this, I have 1/2 mr squared times v squared divided by r squared. My r squareds can cancel out, leaving me with 1/2 mv squared plus 1/2 mv squared. Now, if I look at conservation of energy, I don't know why I didn't go one step further yet, but I didn't. If I look at conservation of energy, I can say, I know conservation of energy says my energy at the top equals my energy at the top, right there, equals my energy at the bottom. And therefore, mgh equals 1/2 mv squared plus 1/2 mv squared. Now, every single term has an m. So if I divide everything by m, there it goes. And a half squared plus a half squared. A half plus a half, 1/2 plus 1/2 is 1. So 1/2 v squared plus 1/2 v squared is simply v squared. And if I square root both sides, I can solve for the velocity. Any questions there? I'm apparently energetic today. When I get energetic, I sometimes go faster than I mean to. So let me know if I go too fast.
How did you cancel out the two r squareds?
How did I cancel the 2r squareds? And sorry, I just realized, sorry, I'm going to do a quick other thing because I'm accidentally not using the headphones I'm talking into. So that was barely heard. Now I can hear better. How I did is because I have, it's r squared divided by r squared, right? This is m r squared times v squared. And I wrote it as m r squared v squared over r squared. But that's the same as m r squared v squared over r squared. That one r looks really
Ah,
crappy. Let me redraw
right,
it.
right.
It's the same idea. And so I have r squared divided by r squared. They cancel out. That make sense?
Yeah, thank you.
Okay. Any other questions? Okay. Let's do the same problem. Instead of a hoop, like so, the first one's like, you got this. The second one's saying, let's say we got this. We got a disk. If I have a disk or a solid cylinder, some of this logic will stay true. The difference between, why are you not doing what I want you to do? The difference, though, between my hoop and my cylinder is that the moment of inertia of a hoop is mr squared. The moment of inertia of a cylinder is 1/2 mr squared. And so if I have a cylinder, my moment of inertia is different. But I still can say my energy at the top is mgh, and my energy at the bottom is linear kinetic plus rotational kinetic. And I'll still plug those in. It's just now I'll say the energy at the bottom is 1/2 mv squared plus 1/2 mr squared, v squared over r squared. There's an extra term in there. Just like before, I'll factor through my squared. Just like before, I'll cancel out my r squared. And that leaves me with 1/2 times 1/2 v squared, or mv squared. And a half times a half, that's a quarter. And just like before, I'll say E top equals E bottom. E top is mgh. E bottom is 1/2 mv squared plus 1/4 mv squared. Just like before, I'll divide both sides by m. Now a half plus a quarter, if I'm going to do that math, a half plus a quarter, I know 1/2 is 2/4. So a half plus a quarter is 3/4. And if I multiply both sides by 4, divide both sides by 3, and then square root, I can say my velocity is the square root of 4/3 gh and get a value. Questions? Okay. Here's the interesting thing. I said that this hoop and this disc, the hoop and cylinder, I should be consistent calling it disc and cylinder, at the top of this hill have different velocities at the bottom. You can actually see this. What I have here is I have a hoop and a disc. I have a hoop and a cylinder. So there's my hoop, there's my cylinder. These are made out of various materials of various densities, so they actually have the exact same mass of each other. And they actually also have the exact same radius. And if I let go at the same time, you can see they don't stop, land at the same time. That the disk, the solid disk, gets to the bottom a hell of a lot faster. It gets to the bottom faster because it gets a higher velocity. Because it doesn't take as much, it doesn't use as much rotational energy, so therefore it can get more linear energy. That the shape of something will affect how fast it rolls down a hill. And if you have rolling, you need to incorporate the shape because you have to incorporate the kinetic energy due to spinning. Questions? Does that make sense? Okay, I got to make some notes. I'm gonna make a slight change to that slide, but that's on me. Okay. As of now, in chapters 1 through 6, we covered kinematics, more kinematics, forces, energy, momentum. I said in chapters 7 and 8, our goal is to do everything again rotational. And so we did the angular kinematics equations. Then we did torque, which is basically angular forces. Then we did angular energy or rotational kinetic energy. I haven't touched on momentum again yet. We did momentum in chapter 6, but we haven't talked about what momentum means when something is spinning. So let's look at momentum or angular momentum. When we first introduced momentum, I introduced the impulse momentum theory. That impulse has two different equations. One is force times time, and the other is change in momentum. So force times time is change in mv. And what this said is that if your impulse is 0, you have conservation momentum, which was the fancy way of saying that if you have a collision and no third object comes running into the side, intercepts it, and hits it, that if you have that setup, momentum is conserved. Well, I'm going to take this equation up here, this F delta T equals delta mv, and I'm going to multiply both sides by all. If I multiply both sides by all, I get all Ft equals all mv. And let's just move that all into my delta. And what I'll say is all F times the change in time equals the change in all mv. You see, before, where impulse caused the change in momentum, where force times a time period caused a change in momentum, I'm going to say all F times a time period causes a change in whatever the hell all mv is. But all times F, that's a simplified version of torque. Torque, as we know, is all F sine theta. So just all F is just torque assuming they're perpendicular. And if we could say that this equation right here means if impulse is 0, momentum is conserved, that means this equation means if torque is constant, all mv is conserved. And that all mv, we are going to call it angular momentum. It has units of kilogram meter squared per second. Now, OMV is a little more complicated than you'd want to do for angular momentum. To do that equation correctly, it really should involve a whole bunch of vectors where it will be m all cross v with some cross products involved, or is it v cross all? It's been a few years. But instead, since we don't want to deal with calculus, I'm going to just take that equation, OMV, and I am going to put an extra factor of all. See, OMV is the same as m all squared times v over all, because one of my o's can cancel out. And m all squared, that's our basis for conservation. Sorry, that's our basis for moment of inertia. And v over all, that's angular velocity. And this is the equation we're going to use for angular momentum, because once again, we don't want to use the OMV when that involves calculus. what we can say is angular momentum, which uses the symbol L because fucked if I know, is equal to moment of inertia times omega. Well, linear momentum, which has the symbol P for the same reasoning I just gave, is mv and is a vector. We'll say angular momentum is I omega. Instead of momentum is inertia times velocity, we're going to say angular momentum is rotational inertia times rotational velocity. I mean, I should say angular velocity, but I'm trying to get the idea across. Officially, it is also a vector, although I didn't mark it here, and I'm going to get to what vector notations of it. Really understand the vector, though, you got to get back to that calc idea. So any questions so far? What this says is anytime the net torque on something is 0, angular momentum is constant. And the conservation of angular momentum just says, I mean, I wrote the same thing here twice in different ways, that if you apply no external torques, angular momentum does not change. This is so useful. This fact will allow us to do many, many, many things. Some just for fun. This football is why I'm playing with a football. We're going to talk about it there in a second. Some slightly more practical. But as long as there's no external torque, which means if something is spinning, as long as something doesn't come in from the side and smack it. Like if I throw this football and just smack it down when it's in the air, then everything's out the window. But if no external torques happen, angular momentum does not change. That moment of inertia initial times angular velocity initial equals moment of inertia final times angular velocity final. So, some uses of this. One of them is a football. See, as I said before, angular momentum is actually a vector. And it follows that right-hand rule thing we talked about at the beginning of the chapter. So if I throw a football and spin it like this, I can say it has an angular momentum vector. Well, I call my direction the direction it's going, and my thumb points at the direction. When you throw a football, you don't just kind of want to go like, but you want to throw a spiral. The reason you throw a spiral is if a football is spiraling, it has angular momentum. If it has angular momentum, it doesn't want to change. And so something spinning will go through the air straight or further. That a football just bare will not go as well because it has no angular momentum. But if you give a spiral, if you set it spinning, once the football is spinning, it has angular momentum. Because it has angular momentum, what's going to happen is it'll want to go in a straight line. This goes back to the James Bond intro picture. We talked about rifling on last chapter. We talked about rifling last chapter. That bullets are made to spin. The reason why is so they go straighter. They have angular momentum. This is also how a bicycle works. If you have a wheel and you just put it upright, it's going to fall, right? But if you hit the wheel spinning, it'll stay upright. The reason it'll stay upright is because if it's spinning, it has angular momentum, and angular momentum doesn't want to change. And so a wheel or a bicycle or a motorcycle or a unicycle, for all I care, will stay upright and not fall to the sides because it has angular momentum. And this is also the basis of most tricks done in gymnastics, figure skating, and diving. And this is where it gets a little more interesting. See, let's say I take this ball and start it spinning. And I'm going to have it kind of loose in this hand. I'm not going to like grab it tight here, but just kind of have it loose. If I set this spinning, right now it has a certain amount of angular momentum. The angular momentum is going to be based off its moment of inertia, mr squared, times how fast it's going. If I suddenly make the radius smaller, it suddenly started spinning faster. That here was spinning kind of slow. When I pulled it in, it sped up. See, what happened was angular momentum was conserved. When I decreased the radius, I increased omega because I omega initial equals I omega final. If you watch figure skaters or gymnasts or divers, what you'll see is when they want to do something with a spin, they start with their arms out and they begin the spin with their arms out and then pull their arms in. When you pull your arms in, what you're doing is you're rapidly decreasing your moment of inertia. You're decreasing your moment of inertia because you're decreasing your radius. And if you decrease your radius, if you decrease your moment of inertia, you must increase your angular velocity because it's conserved. I mean, here's me on a spinning platform. I have my arms out, I spin slow. I pull my arms in, I spin faster and almost fall over. Arms back out, I go slow again. This is one of the few things I'm happy to not do on live in class instead show a video, because normally I get super dizzy in class and almost fall over doing this chapter. That's the idea. And then once again, that's what gymnasts do, divers do. They just start spinning with their arms out, and then they pull in, they go faster. I just said I was happy I wasn't going to get dizzy. That is the idea.
I really enjoy your videos. They're really like entertaining. I love them.
Oh, thank you. Normally they'd all be done in the front of the classroom. So okay. Let me show you a kind of interesting example with this. You see, angular momentum is really a vector. And so what I'm going to do is I'm going to take a bicycle wheel and set it spinning on the horizontal plane, like so. And I'm going to do it while the picture shows someone sitting in a chair. I'm going to do it standing on that platform I was just on. And what I'm going to do is if I set that spinning, I have a certain amount of angular momentum. I don't, but the wheel does. And angular momentum is a vector. If it's spinning the correct way, let's say my angular momentum is up. What I'm going to do is I'm going to turn the wheel upside down. So here we go. Wheel, spinning, stand on platform, and flip. The second I flip it, I start spinning. When I put it back, I stop spinning. Flip it again, there I go again. I think I'm wearing the same shirt. No, I'm not. The reason why is conservation of angular momentum. That right now, I have a certain amount of angular momentum. When I flip that, I have to have the same amount of angular momentum. And that when I bring this wheel upside down, right side up, and whatnot, my angular momentum will not change. An interesting thing, if you ever get something spinning and you like can hold it in such a way that it keeps going, try moving it around. You'll find it's difficult. It resists it. That if I take a bicycle wheel and just do that, normally it'd just be like, woo. But when I do this spinning, you can kind of see the way my arms move, that it's not like easy, that I kind of like a little bit. And this is the reason why angular momentum is conserved. See, when I flip that wheel has a certain angular momentum. And I'm going to say the angular momentum of the wheel, I'm going to call the wheel 1 initial. When I flip it, I make that vector point in the opposite direction. If the vector points in the opposite direction, that means my final angular momentum is just the initial times the negative sign, because it's now pointing in the opposite direction. But my total angular momentum must not change. Which means if my total angular momentum doesn't change and it goes from a positive value to a negative value, it means I have to add some new large positive value. I start spinning so that my total angular momentum is conserved. Keep in mind that my L1 final is just negative L1 initial. And that's why I spin. Does that make sense?
Barely.
Surprisingly.
General idea is angular momentum is conserved. The total angular momentum doesn't change. And so if I suddenly try to change the angular momentum and I take the wheel and give it a different angular momentum, suddenly I get angular momentum so that the total is the same. That's the idea. I'm going to do one more video demo This is another one I would normally do in class, but you know, life sucks. This one I really can't fully explain without calculus, and I'm going to acknowledge that, which makes it kind of stupid to do in class, but it's so goddamn interesting, I'm doing it anyways. Let's say I take my bicycle wheel and I attach a string to one side. When I attach a string to one side and it's just loosely there, like nothing's holding place, when I attach the string to one side and let go, the bicycle wheel is just going to fall, right? The reason the bicycle wheel is going to fall is I can say there's a force on the wheel from the center of the wheel, the center of mass, which is right here. And what I can say is that the wheel is held up by the string, and there's going to be some torque, where torque is all F sine theta. You see the center of mass is a distance all away, and the force is down. In chapter 6, when we did momentum, we said impulses change in momentum. And now I'm saying torque times time is change in angular momentum. Well, here's the thing. I'm glossing over these things called cross products in here. That vector algebra for rotating things is very weird. And you see, when this spins, I will say its angular momentum is going to be following this right-hand rule idea, either in the direction that this L arrow shows, or it could be in the opposite direction if it spun the other way. And if I do apply a torque, because here I can't use conservation of angular momentum, torque is being applied. A torque due to the force of Earth is being applied to this wheel. And if I apply a torque, what this says is if I apply a torque, my angular momentum changes. So if I just drop this, it just falls. But if I spin it, the torque that is the force of gravity, the torque that is this yellow R times this green F, will change the angular momentum. And what's going to happen is that when this is spinning, which spin, instead of just falling, it precesses. It stays upright and doesn't fall down. It just spins in a circle. Now you can see it's starting to slowly droop down. That's because the wheel is slowing down due to friction. As there's friction in the bearings, as the wheel slows down, it'll start falling. But because of angular momentum, the wheel stays upright. Same idea as the bicycle. That the bicycle wants to stay upright, so does the wheel. And even if I only attach it on one side, the wheel tries to stay upright. Because all the torque due to gravity is just going to change the angular momentum. And that's why. Normally a torque causes a change in angular momentum. Since the angular momentum is pushing perpendicular to the wheel, it's just going to cause it to spin in a circle. As I said, that really gets into something more complicated that involves a little bit of calculus, but I just wanted to show that idea.
That's the best thing ever, honestly.
This video here, you can watch it on if you want. It's someone doing with like a 50-pound weight at the end of like a 2-meter thing, and they're trying to get people to see if they can lift it, and no one can lift it, and they set it spinning, and then the guy can lift it easily because gravity goes to not pulling it down but making it spin. As long as that's the video, I think it is. I think it is.
This is
Is
how
that
the
like Veritasium or something?
Say it again.
There's some YouTuber called Veritasium. I've seen
Yep,
him do
that's
something
him.
like that.
That is him. Yep,
It's
that is
wicked.
exactly who that is. And if we have time today, I'm going to show a different one of his videos, actually. Okay, let's do an example problem. This problem is from the exam. And this problem is going to cover angular momentum. But is also going to, I said the problems on this exam are going to kind of mix topics. This problem, as written, covers things from chapter 7 and this angular momentum idea, and some stuff from earlier this chapter. This is going to be all over the place. Let's go through and solve it. Son Goku is from the classic Chinese novel. I'm blanking on the name of the actual original novel. I'm blanking on what it's called. It has a name.
To the West.
But say it again.
Journey to the West.
Yes, Journey to the West. Thank you. And Dragon Ball Z, Goku from that is a Japanese version of it made to anime. Son Goku is much, much, much older than Dragon Ball Z. But in both the classic story and the anime, he has a magical staff that can change its length. There's also a Goku in Naruto with a magical staff who can change its length, kind of in a weird way, the Hokage. So let's say Goku starts with his staff being 0.879 kilograms, or it's always 0.879 kilograms, doesn't change mass, but it starts 1.86 meters long, and he spins it around the center. How he spins it around the center is by grabbing at a pivot point and applying a force some distance away. And so I say he applies a force of 5.48 newtons, 0.465 meters away from this pivot point. He basically holds it solid here and pushes there. Kind of how you spin a staff. You pivot around one side and push the other. What is the angular acceleration giving the moment of inertia staff around its center? If he uses that angular acceleration, how fast is it going after 5 complete rotations? And if he then makes it smaller, what's the new angular velocity? Let's go through. What I know is this staff has a mass of 0.879 kilograms, has a length of 1.86 meters, and he applies a force of 5.48 newtons, 0.465 meters from the center. And it says, what is the angular acceleration? If I ever want to solve for angular acceleration, I have two options: kinematics or torque. Anytime you see time or angle will always be kinematics. Neither time nor angle is given here, but moment of inertia is. So I'm going to use torque. Torque is RF sine theta. Now I didn't give an angle when I just wrote, but I did say perpendicular. So my angle is 90 degrees. So my torque is RF. And I know the sum of torques equals I alpha, which means RF equals I alpha. And I can solve for alpha, my angular acceleration, because my angular acceleration is RF over I. As for I didn't explicitly give a I, but I kind of did. I said the moment of inertia is 112 ml squared. So that's I, which I can solve for. And allow me to plug in my values for alpha. That's the angular acceleration. Questions on part A, which has nothing to do with momentum yet? Part B. He keeps up that angular constant acceleration. What's the angular velocity after 5 revolutions? Assume he starts from rest. Okay, if he starts at rest, omega naught is 0. And he went through 5 revolutions. 5 revolutions is an angle. It's in stupid units. I need to convert it to radians, where 1 revolution is 2 pi radians. So screw 5 revolutions, 31.4 radians. But that's still an angle. Anytime you have an angle, use kinematics. See, what I can say is that angular velocity squared is initial angular velocity squared plus 2 alpha theta. And since he started at rest, I can just say his angular velocity is the square root of 2 alpha theta. And I now know alpha. So I'll plug in and solve. That's from last chapter. You still good? Part C is the new material. Part C says, Goku then shrinks the pole to a length of 1.2 meters while no longer applying any torque. What is the staff's new angular velocity? And so what I'm saying is he's spinning some long staff and then it goes whoop, and gets shorter. Anytime you see something with something changing mass or changing length or changing radius, And because of a change in radius, a change in speed, that is angular momentum. Changing mass is a lot less common due to the law of conservation of mass. I can only do a problem with changing mass if I do something fictional. There's a problem on your homework with Ant-Man because Ant-Man's mass changes sometimes. I love how in the movie they say his mass doesn't change, but then they show him like crawling on people that they're not noticing. And if his mass didn't change, it would be like a person's weight on your shirt. You'd notice. Anyways, sometimes his mass doesn't change. They go arbitrarily back and forth with it. But if you see something changing mass or radius and therefore changing angular velocity, that'll always be angular momentum. And so what I would say is initial angular momentum equals final angular momentum. Well, angular momentum equals I omega. That means I initial omega initial equals I final omega final. And you might have noticed all my numbers at the top for my I and my omega, I added an initial symbol just to make sure we realize those are the initials. You see, if I want to find this angular velocity after it shortens, I'll just divide both sides by I final. I mean, I do still have to find I final, but I final is still 1/2 ml squared. I'll just use the new value for L and get a new value. And that'll allow me to plug in and get a value. And it will go from 25.1 radians per second to 60.4 radians per second. Questions?
Where did 112 ml squared come from?
That is just the moment of inertia of a long rod. I just kind of gave it in the initial. I said assume the moment of inertia is 112 ml squared. But if you want to actually see where it came from, it would be one of the last few slides from Monday's class, where the moment of inertia of a thin rod is 112 ml squared.
Oh, right.
I don't expect you to know these. I will always give them.
Oh, thank you so much.
They're actually not too bad to calculate using something called the parallel axis theorem, but honestly, to do it, you need to take an integral. Part of the reason I never expect you to do them. Be happy you're not doing the calc-based version of this class. Any other questions? Okay. That's chapter 8. In general, doing everything in both chapters 7 and 8. Chapter 7 and 8 is kind of all the same equations. It's just every F becomes a tau. Every M becomes an I. Every A becomes an alpha. Every V becomes an omega. Every X becomes a theta. That's the short version. The secret to angular for problems is you just do the linear one with Greek letters, except for the I. I don't know why I doesn't get a Greek letter. That's the idea. Okay? Now, you got 7 minutes left in this class, and I finished the chapter, which means it's a good time to talk about next Friday. As I said before, next Friday, there will be an exam. So like always, I'm going to give you a quick version of, well, like always, I only did this once before. I'm going to give a quick version of what you need to know. And I will go in a lot more detail Monday. This Friday will be practice problems. General idea. The first problem will involve energy. I have a lot of equations for energy, but I usually don't include work, so I wouldn't worry too much about work. What you really need is conservation of energy. Initial energy equals final energy, where energy is kinetic energy plus potential energy. And remember that kinetic energy and potential energy each have two forms. You don't always need both. Your first problem might involve a spring. Think the sonic problem I did in class and me on a pogo stick. Or the Luffy. Was it, did I, that's what I did in class? Yeah, I did the One Piece, Luffy, the guy bouncing a cannonball off his stomach. Or I might involve something rolling. Thinking the demonstration I did today with the hoop and the disc, or like the one that you're going to see in class Friday that you haven't seen yet that's about Donkey Kong. Your second problem will be conservation of momentum. In a collision, initial momentum equals final momentum. Well, momentum is m times v. Theoretically, I could go two-dimensional, which makes it more complicated. But spoiler warning, I've never done two-dimensional before. I'm probably going to not start now online. The last two problems, problem 3 and 4, will be a mix of 7 and 8. Be prepared for kinematic equations. Not only kinematic equations, but the link between linear and rotational. And don't forget that 1 revolution is 2 pi radians. Also be prepared for centripetal acceleration. And be prepared for torque. And also be prepared for angular momentum. Sometimes this equation also shows up in either number 7 or 8. Oh, sorry, in problem 3 or 4, but it more often shows up in problem 1. Any questions? Okay, there you go. That's chapter 8. Don't forget your homework due tonight. I'll see you all Friday. Have fun. Bye.